Next presentation is from Max. This might as well have been an invited talk because I already saw 2 citations to this work in this bridge today.
Thank you so much. Can everyone hear me? Yeah, all right, great. So yeah, today I'm Max with Francisco, my co-author, to talk about our work and our ideas for building more rigorous PDDL generation benchmarks, or if we want to be a little more cheeky with the title, defining it in PDDL would be something like this: goal PDDL or benchmark PDDL generators. So let me just quickly recap again the different ways that LLMs have kind of been used for planning. I'm going to be very generic and just put them into 2 buckets. So in the first bucket, we kind of have LLMs as planners, right? So here we have some sort of planning problem that gets fed into the LLM along with some domain information, and this is used to directly output the plan, right? And so the planning problem, if we're going to be generic, it can be in natural language, it can be in PDDL, and same with the domain. There are techniques that use it in both natural language and PDDL or some sort of other specification. And the plan can be a pretty flexible format as well. But generally speaking, like the idea behind this is the idea for the LLM to do the actual planning and the LLM to be this sort of end-to-end solution. And you kind of run into some issues, right, where the LLM doesn't give you certain guarantees or certain features that you might want or you might expect. Right? Like you can't guarantee correctness a lot of times, you can't guarantee optimality a lot of times. And so, yeah, there's been a lot of works citing Valmikam and Rao again on how LLMs are not super suited to plan directly. So there's this other category called LLMs with planners or LLMs augmented with planners. And the idea is we feed it some natural language planning problem and we feed it domain again, but instead of directly outputting the plan, we output this problem PDDL specification, some formal specification of the problem. And this can be fed into a planner downstream, and that can produce your plan that you want. And so what's nice here is there's some sort of natural division of labor between the two things where LLMs are really good at phrasing things and they're really good with language, right? And they're really good with like code generation tasks, for example. You can kind of see like natural language to PDL as a form of code generation or a form of like translation. So that's something that LLMs are pretty good at. And then we can kind of get to use planners and have the sort of guarantees that we're used to, that we've spent like the planning community has spent like decades on trying to build and ensure optimality and correctness or different other characteristics that you might want with planners. And something that's nice about this too is we don't have to have a planner doing the evaluation step. We can potentially just evaluate on just the problem PDDL output. And the problem PDDL is going to capture a lot of intricacies of the problem that maybe an individual plan might not capture. And so a notable work in this area is LLM plus P, where they looked at LLM generated PDDL and evaluated it. So let me talk a little bit about how to actually evaluate PDDL, right? So let's say we have this problem here where there's an initial scene, there's 2 blocks on table, robot arm. This is classic blocks world, and we want to stack them, right? So we can't just feed this abstract idea to an LLM. Of course, we build a prompt for it. It'll look something like that. It'll say what I just said. We have 2 blocks, describe the initial scene, then describe the goal scene, and we feed this into the LLM, right? So this is what we feed. And what we expect out of it is some sort of PDDL specification. So let's assume that the initial state is correctly defined. What does the goal specification look like, right? So the goal specification in this case would look something like this. Okay, so the arm is empty. All right, so let's have that. And now there's 2 blocks, and we didn't really give them names during our prompt. So let's say the LLM just decides to pick the top one to be A and the bottom one to be B. So the top of A is clear. Now A is on top of B and B is on top of the table. So this fully encaptures our idea of what the problem is, right? Like all the relationships are kind of explained in here. So this is like a good gold standard of what that might look like, what a goal specification might look like from an LLM when it's correct. So what are the different ways it can be incorrect? Well, the simplest is just we have, okay, some typo. That's fine. That's quick and easy. We can check that. We can detect that with a parser, guarantees correctness. It's fast. Now, what happens when it's parsable, but it's not solvable? It can produce this, right? This is something that it can produce where B is on top of A and A is on top of B. We're not going to be able to solve that, right? But okay, fine. We feed this into a solver and it tells us there's no plan that can solve this. All right. So the next part is something that like prior works are kind of missing, which is like what happens when the thing that it produces is solvable, but it's describing a completely different problem, right? So here it's saying on table A. So A is on the table, but that's not what we want. We want A on top of B, right? It'll go through a solver, it'll produce plans, but it's not describing what we want. All right, so those are like the different ways that PDDL generations can be incorrect. Let's go back to what a correct generation looks like. But this isn't the only correct generation, right? There's a lot of different ways that we can specify the goal that's still correct. For example, we can permute these propositions, right? That's fine. That's still describing the same goal. We can also have the LLM rename things. If we didn't specify a name, the LLM could have, for example, named A O1 and B O2, and that's fine. And we can also kind of remove some of these predicates, and they're still going to be describing the same kind of problem. If I just leave this on here where it just says A is on top of B, well, every problem that solves this goal specification from the initial state is going to solve all the other correct specifications that we've mentioned before. So just as a recap of this first part, PDDL generation is important, it's great. We should keep looking at it because it lets us use the tools that we've built for ourselves in the last few decades. And PDDL correctness is kind of hard to evaluate, right? It's more than parsability. It's more than just checking solvability. And it's not like it's something that we can just have a ground truth string. That's something common in like training LLMs to have and compare character to character, right? We can't have like a ground truth PDDL file and just compare the files together. So that's where Planetarium comes in, Francisco, and my work. Planetarium consists of a data set that we contribute, which is 145,000 natural language and PDDL problem pairs. And that covers the blocks, world, gripper, and floor tile domains, more or less the IPC definitions. And we build an evaluation algorithm where we don't work directly with the string or PDL, whatever. We convert it into these problem graphs, and we kind of reason about things symbolically. And then finally, we use that evaluation algorithm that's a bit more rigorous than just using a solver or planner or parser, and we evaluate some LLMs. So to quickly go over the data set, I'm going to show you a prior work. So on the x-axis are two different measures of problem scale, how big a problem is. And the y-axis is in log scale, the number of problems in the data set. So prior work had a good number of problems. And our work, we introduced a lot more problems. But notably, like I want to point out that we also work with a lot more bigger problems. And we're able to evaluate on those bigger problems very, very quickly. And this is a better stress test, in our opinion, of LLM's capabilities of understanding problem specifications. And so for the experimental setup, we try to measure these three things. So parsability, which is what I talked about before with syntax errors, solvability, if it can be solved by a planner, and correctness, if it's actually describing the thing that we want it to describe. And we evaluate several models. We evaluate the Gemma 2 family of models. So we either do it in zero-shot setting or we do it in a fine-tuned setting. We do GPT-4o, and finally we do O1 mini. And we test this on a set of 16,000 problems. For the fine-tuned models in Gemma 2, we hold out the blocks world, some blocks world and gripper tasks, so individual tasks that it's never seen before, and we hold out the entire floor tile domain. So I'm going to show you the results now. So for parsability, like, yes, great. GPT-4o and O1 are doing really, really good. They do a solid job of producing parsable text, parsable PDDL text. The Gemma 2 family don't do quite as well. This is the 27B, which is the biggest and best at the time. Solvability, it's a little different. It's more or less the same, right? But when we look at correctness, there's a huge jump difference between something that's correct and something that's solvable. So that's showing like the measure that we're looking at is important, right? So prior works, we're looking at solvability. We're looking at correctness. And if you look at correctness, you see that, yes, these models are great at generating PDDL, but they're not generating the PDDL that you want it to generate or you care about. And yeah, this is like the big conclusion of our paper. And just as a summary, like PDDL generation and evaluation is key if we want to continue to use the tools that we had built and the benefits that come from them. And as important as it is, we hadn't been doing it properly in the past. And when we do look at it properly, we see that LLMs seem like they perform well, but they actually don't perform as well as you might think. And that's it. Our data set is up on Hugging Face, our code and paper on GitHub. And we'll be presenting this paper at NACL, so you can see Francisco there.
Take a break and then we start again.